Hi and welcome back. So in this video we're finally going to be explaining the linear time solution for the valid anagram problem. So let's get started. Again, let's recap quickly what the last solution was. We have the word S and we have the word T. So S is made of several letters, right? We said we have several letters in S, and T is also should be, if T is an anagram of S, then it should also be made of the same number of letters, and we should have some sort of matching. For each letter here, there should be a matching here. So the idea of the new algorithm is, okay, let's have a hash table, okay? And then in this hash table, I'm going to say, okay, I'm going to have letter, and I'm going to have count, okay? So what are the possible letters in the letter S? So we can have A, B, C, D, E. If we look at the problem here, it says you can have the letters are, you may assume that the string contains only lowercase alphabets. So what can we do about that? Well, one way is we say, okay, let's say S is an anagram. Anagram, right? So before, and T is, again, Nagaram. So we start saying, okay, I'm going to put the letter A here, the letter B here, the letter C here, and all the way all to the letter Z here. And then I'm going to say, okay, how many times is the letter A shown in anagram? Well, I know that there's an A here, and an A here, and an A here. So there's 3 times. How many letters are there in B? So none. So I put a 0. How many C's are there in anagram? None. 0. And I do the same thing all the way to Z. So Z has 0 because we don't have any Z here. So after I've filled this hash table for the word S, I do the opposite for T. So I say, okay, how many letter A's are there in T? So instead of adding +3, I'm going to do -3 because I have an A here, an A here, and A here. So 3, I take away 3, so now it's 0. And then B, there are none here, so I wouldn't take 0. So -0, 0 minus 0 is 0. And then C, there are no C's here, so I just 0, and I do the same process for all the letters. So you can see here that if by the time I'm done with all the letters in T, subtracting, like let's say I found an N, so subtract 1 from N. Let's say I found A, so -1 from A. G, -1 from G. A, -1 from A. By the time I'm done with all the letters, then this hash table, if T is indeed an anagram of S, then this hash table should return to 0. So let's take another example. If S is A, B, A, C, and T is A, B, C, A. Okay, so the hash table would have 2 columns, correct? The letter and the count. So let's say A, B, and C, and we don't need all the letters all to Z, but we can also add them just if you want. Now, how many letter A? I start by handling S first. I say, okay, S, there's an A, so 1. B, so that's a 1. A, so there's already a 1 here, so I change that to 2. I add 1 on it. C, oh, I make this 1. And then, again, now I go for T, and I say, oh, A, so -1. So -1, 2 minus 1 is 1. And then, oh, B, so -1, 0. C, -1 is 0. And A, -1, which is here 1, -1 is 0. So we'll see that all the table is actually 0. It starts with 0. And this is, of course, initialized to 0. All the other letters are initialized to 0. So using this process, we can sort of just have a hash table of size 026, which is just 01 space, and we go one time over all the letters in S, add ones, and then go one time over all the letters in T, subtract one, and then if all the counts is 0, then we return true. They're indeed anagrams. If they're not, then we return false. So how would that translate into code? So first of all, we're going to do let H, so let H be an empty hash table, initialized to 0. Now what do? We say, okay, for I 0 to the length of S, and then I simply say H SI plus plus. So I'm increasing the letter with SI. And then, once I'm done, I go another loop for I0 to length T this time, and then H of SI, or TI, sorry, minus minus. So I'm taking away 1. And then I go through a loop, so for I0 to the size of H, if HI is not equal to 0, then return false, because we found one that hasn't been reduced to 0. But if I go through all this loop and everything is fine, then I can simply return true here. And we're done. So in the next video, we're going to see how we can sort of implement this pseudocode into programming languages. Hopefully it's not too hard to sort of translate. And again, let's finally take an example where this wouldn't work. So let's say ABC and T equals to AAA. So obviously these two words are not anagrams, right? So if I start handling the table, I would have a table, the H table. I would have the letters count, and then for S, once I finish it, I'm going to have A with 2 and B with or A with 1, sorry, B with 1 and C with 1. But then after I take away 3 for the T, this is going to be -2. So obviously here, you know, this is -2, this is 1, this is 1. All of them are actually not 0. So if we find anyone which is not 0, then we simply return false. These words are not anagrams. But if all the letter counts are 0, then we simply return true. So yeah, in the next video, let's start implementing that. So until the next video, happy coding.